Okay, welcome. This is a new experience for me. I've given lots of talks, but I've never done a YouTube live. I assume that you can see my screen and my video in the top right corner, but I have no way to really check this. In particular, you are also about 30 seconds behind me. So therefore, even if you are watching live, you cannot easily ask questions in the middle of the talk. So I suggest we do the following. You save your questions for the end. I will have a question and answer session using the live chat, and we'll have to see how this works. So therefore, I will keep talking. So the plan for this talk is that I'm talking about the application of a multi-model database, ArangoDB, in a sample which is a little data model for an e-commerce app. So I will introduce the idea of native multi-model database in the beginning. So I have a few slides to just talk, but then we will jump directly into action. I show you live and on a database which is running the data model, which is one possibility to run such an e-commerce shop. Okay, let's get started. This is supposed to take about 45 minutes altogether, but the first part will be really brief. So, the idea of a multi-model database, or actually a native multi-model database, is that it is a data store which combines a document store, a graph database, and a key value store in the same database engine. And the most important thing is that it's not just three things put together, but that there is a common query language which is able to talk about all these three data models and actually even mix them in a single query. So the selection of document store, graph database, and key value store is a very deliberate one, because this combination enables us to don't make compromises because of the combination. So ArangoDB, or such a multi-model approach database, can actually compete with a specialized document store, or with a specialized graph database, or with a specialized key value store as a special player. But in addition, it allows you to have a lot more use cases where you use all the data models, or it allows you to do the famous polyglot persistence, by which we mean you can use the right data model for the right part of your product. Or if you have a microservice architecture, then you can have different microservices using different instances. But since the database, the same store, offers multiple data models, you can use the right data model and still have only one technology deployed. There might be several different deployments of the same technology. That's what you would do in an architecture like this. But it is still the same data store. So therefore you have the license costs, the education costs, and the maintenance costs, and the upgrade costs, and so on, just once. So that's the idea. And the thing, what happens in recent days is that many data stores call themselves multi-model database, but mostly they have a single data model and have, in a bolt-on fashion, on top of that, different personalities. And the word native multi-model days refers to the fact that everything is designed from day one on to be integrated in the same store with the same query language using all three data models. Let me just give you, aside from the example I'm talking about today, another use case which makes use of the multi-model nature of ArangoDB. So this is about aircraft fleet management. In this use case, a customer of us has to manage an aircraft fleet, and obviously an aircraft fleet consists of airplanes. But airplanes themselves, then they consist of subparts, and the subparts of smaller sub-subparts. For example, the aircraft would have the engine as a part, or one of the engines, and then the engine would have subparts, and down to the last screw. This is actually a very large hierarchy of things. And what turned out in this use case is that a very good way to do the data model for this was to store each part, component, unit, or aircraft as one document. And the containment of these parts or components is modeled as a graph. So why was this important? The thing people were struggling in this use case were that a lot of different queries came up in the project. So just to say a few, for example, it was necessary to find all the little parts which are in one component. What do you do in this model? Well, you take this tree of things and you just do a graph traversal downwards to enumerate all parts which are contained in one component. Another problem which arose was to start from a single piece, say a screw which is broken, to find the smallest component it is contained in, which has a maintenance procedure. So therefore we had to go up in the graph and find the smallest component, the smallest document, which has a maintenance procedure. And in other cases, so this was again, of course, done with a graph structure. In other cases, you need to do something which is completely orthogonal to the graph structure. So, say, for example, among all the aircraft or all the things, just find something which has maintenance due next week. Yeah? And this needed to ignore the graph structure. And it turns out that all of these queries can be done with good efficiency with this data model. Some of these actually have to mix different data models, like doing a join operation, doing a graph traversal, and doing a key lookup in the same query to be efficient. And actually any other data model that was tried, a relational model or a document model or whatever, didn't manage to get all the needed queries to be efficient. And so this is an example where the true native multi-model approach was needed to get the whole project done. I've written a blog post which is linked on this slide about the details, and you're welcome to have a look. Just let me know that all the material, all the slides, all the code examples, and obviously the video will be available online later on, so you can go to YouTube and download the video and watch it. And from there, on the comments page, you will find the slides linked and the material, so you don't have to take notes or whatever, and nothing gets lost. And if you have the slides as PDF, then these blue things are actually links which you can click. Right, so before we move to the actual use case I want to talk about today, let me just say why this combination of data models works at all. So why have we picked the document module, the key value model, and the graph model and combine them? Why didn't we pick time series, or why didn't we pick a columnar store or the classical relational model? Well, the answer is that these three fit together, and I want to show you in 2 slides why this is the case, just to give you an idea. Well, if you look at what a document store traditionally is, well, documents means document in the same sense of JSON documents, but nearly all document stores, at least those I know, always store their documents in something called collections or otherwise, but where there is a primary key. So in a sense, a document store is a key value store where just it so happens that the values are JSON documents. And since JSON is a very versatile format, you can essentially encode, if nothing helps, you use base64 encoding for binary data, you can encode essentially everything. So essentially, if you have a document store and you don't use any other secondary indexes, then you can use it as a key value store and store arbitrary opaque values in there, and you have a document store. You have a key value store. this doesn't sacrifice performance, because a document store, if it's done well, which doesn't use any secondary indexes, has the same kind of horizontal scalability, the same kind of performance as a specialized key value store. And okay, there's a little overhead with binary encoding, but this can be neglected. So therefore, document stores and key value stores fit together naturally. Now let's talk about document stores and graph databases. Well, a graph database, let me just stand back a moment and say what it is. Well, a graph is the thing with vertices and edges, where edges always point from one vertex to another, or to the same indeed. And what makes a great graph database is not so much the possibility to store a graph. Yeah? But what makes a graph database really worth its value is that you can query it in a graphy fashion. So you can ask graph questions. So what is a graph question? A graph question is essentially one which makes use of the fact that a graph is something which is linked, and which essentially means you have to follow the links in some way. The most typical way is that you say, I want to start, say, here, and I want to find all ways to do a certain number of steps in the graph and give me all the paths. And then maybe we want to give conditions. And what happens behind the scenes is a graph traversal, that is some kind of depth first or breadth first search, which happens in the database. And the crucial thing for graph support in a database is that you can answer these graph queries quickly. So you need language support, you need a query language which is equipped for this and which can express these graph queries. And then you need to have a fast engine implemented in the database server to do the traversals. And for that, the crucial ingredient is that you need to, from one vertex, quickly find its neighbors. And what we found is that a very good way to implement and model this is to simply store graphs, their vertices and their edges, in documents in a document store. Then have a very good edge index to answer the question, what is a neighbor of this vertex in the forward or backward or both directions, to give you very fast access to the neighbors. And if you then have a query language which implements these graph algorithms on top of this engine within the database engine, then you get good performance. So therefore, the document model is actually a very good way to implement a graph database in the first place, provided you upgrade it with a good edge index and support in the query language. Now, this means these two data models fit together well, and this means all three data models fit together well. And if you can, on top of this, build the facility that you can mix and match these three data models in your query language and even have sophisticated queries which do some part of it graph traversal, some part of it join, some part of it key lookup, then you have a very powerful and versatile system. Now, this brings me to the query language. Maybe you have seen one of the previous talks about this. The ArangoDB Query Language is called AQL, and it reaches exactly the goal I've described before. It gives you the possibility to run powerful, complex queries in a convenient way. It has transactional semantics, so you get a read snapshot of the database, and if you do changes, then you get a write transaction. It can do joins, so it can join one collection to another, and therefore essentially do the same things as a relational data store can do. It can do graph queries as well. And obviously, since it's our own query language, it is independent of the language driver you use for ArangoDB. And we have learned from the bad experience with SQL and have built-in protection against injections. And it is exactly this query language, AQL, which I will show you today by means of example. Right, before we jump into the first query, and I have all my AQL queries which I am using today, before we jump into them, and they are all on the slides, let me just set up things. And to show you that I'm not doing something which requires a great deal of preparation, and to show you that you can do this on your own and play with it, I'm just running everything from scratch here. So with this command, I start locally an ArangoDB instance with a Docker container on my laptop now. So this will take a few seconds, and now I have an empty database to which I can connect via the web UI, which I'm doing here. So I simply type in localhost port 8529 and see that there's an ArangoDB's dashboard, and it's empty in the sense that there's no collection yet. Now let me get back to the command line, and obviously I did some preparations. I use the Arango shell, again running in a Docker container, to execute a very little JavaScript program called shop.js, and you will have access to that after the talk, to quickly set up things in the database. If we go back here in the browser and reload, it reloads automatically, you see here my little data model for the online shop. So this is by no means the only possibility with which you can set up things, but it is one possibility which I think is a suitable way to model the data for this little online shop, and it makes use of the multi-model nature of ArangoDB. So let's quickly study what we have in there. So obviously an online shop has customers. And again, this is only 3 customers. It's just a toy example to really keep an overview and see what is going on. I'm used to the JSON stuff. So that is a sample customer. I just store name, first name, a timestamp for member sins, and an address. And of course, I could have a lot more information. But for every one of my customers, I have one of these. And that's just using the document model. And well, for customers, I could probably use a relational model as well, because the amount of information I store for each customer is probably nearly the same for each customer. Now, obviously, a shop has items. So I have a collection items, which contains entries like this. So here I have the price, I have the number of items in stock, I have something about weight, shipping costs, an order ID, and blah. Obviously, the amount of information I have to store for each item can vary widely. So for example, if Amazon, obviously this is probably not a data model for Amazon planetary size, but still the point is easy to make. Amazon, if it sells a very tiny toy item, then you need to store different information about it than if you sell a very large item which has special shipping provisions and blah blah blah. And therefore the document model is actually quite good to store the items of an online shop. Now what you also need is reviews about your items. Maybe we go there first, because this is just again another collection, and this could be done in various ways, but I've just stored each review in a document of its own in the reviews collection. Obviously it has a key, and it has some text, and it has some rating and so on, and it says what item it is. Note that the item here is just a name. If we go back to the items collection, then this was the key in here. So essentially it is linked, but the actual linkage between reviews and items, and indeed customers, is done with the graph model. So for example, we have here the connection, that's just an edge. It goes from customer Hugo to the review with key 243, and the type of the edge is wrote. So this means in this data model that customer Hugo wrote this review. And if I go back to this review 243, then well, it has a key, but it doesn't mention the writer of the review. Right. And on the other hand, there are other types of links in this graph. For example, customer Lulu actually also has a link from customer to this review, but it is of type liked and has an agreement value. So in this case, the edge tells me that the other customer has actually seen this review by customer Hugo and didn't really agree with it. So I'm using the edge collection for the reviews, the review rel collection, both to encode who wrote a review and who commented or liked the kind of review. Now, maybe the most important connection is the sales connection. And one could argue how to do this, but in this particular example, I have modeled it in the following way. An edge from a customer to an item indicates that the customer bought this item. So for every single sale I do, for every item in the sale, I put one of these links from the customer to the item. In addition, I put a date and I put a billing ID, such that I later, if I need to, can find all the items which have been in this particular sale. I think one can argue about this, whether this is the right data model or not, but for the time being, I would just want to stick with this because it somehow makes the point that there is a good way to do this using the multi-model approach. The final collection is about shopping baskets. This is, in a sense, independent of the others, and it's not actually linked other than every shopping cart has a list of items, but here I use actually embedding. So I put the IDs of the items in there and the number of things, the number of copies or instances being ordered. And you have to think that this is essentially just using ArangoDB as a large key value store to store shopping baskets. Again, this will not be able to handle Amazon scale, but you could imagine that behind the scenes, this is just a cluster ArangoDB, maybe even separate from the other database handling customers and items and sales, just being the back end for the front end, which does the actual selling part. Anyway, so that is my short overview about the data model. And what I want to show you in the rest of the talk is how queries in AQL actually look like if you have this data model and want to program an online shop. And that serves two purposes. One, it serves the purpose of me showing you examples of AQL, showing you the user interface and how I actually run them on this particular data set I have in here. And secondly, it makes the more theoretical point that multi-model and a common query language to cover different data models is actually a good thing, which greatly simplifies your life if you program an app which is like such an e-commerce system. And so that is what we will do essentially the next 20 minutes until this talk is finished. Again, you can ask questions afterwards, and we will see how we can handle this delay of things. Right, all my queries are not only slides in this slideshow, but they are also persisted to a file, and I can run them in the user interface by importing the queries. Hang on. I take this JSON and import them. And okay, it's now a bit large because I have made the writing a bit larger. But I can now actually click on these queries and run them. So what I'll probably do is, before we run them, I will always quickly show the query and explain it on the slide in big writing. And then I will show it in action and see how it's executed and maybe how we can use the query planner and everything. So if you, for example, want to know, show me the new customers since 2016. Remember that we had a timestamp in the member since attribute, and that the year, it was a string, and the year was in the beginning of this string. So therefore, if I use the usual string order, this filter condition filters out all those who are members since 2016 or later. Now, if I give you this query, you don't know AQL, I would guess that you essentially can guess what it does. Well, in a sense, it runs through the customers collection, takes only those whose member since attribute is greater or equal to this string, and it returns the complete object. So this considers only one collection. It is a simple filter collection, and off you go. But this makes already an important point. AQL is a declarative language. You tell, with this language, in this relatively easy syntax, you tell what you want, and the query engine goes away and says, hang on, what does he want? And does a query plan and sees how this can be distributed in a cluster and executes it in the best possible way, maybe using even some estimates about the collections involved and so on. And you only get back the results. So let me run this. So I've just loaded the query. I've here in the preview, and if I click this little button, or if I go over here, if I click this green button, I execute it, and what I get is it was executed in 191 milliseconds. Well, this is true. Anyway, it was executed rather rapidly, and at this stage I have the table view because customers are relatively homogeneous, and therefore it was saying why not display this in the table. Let's look at the JSON output. What you get is simply a JSON array of all the customers, 2 in this case, and remember those are those whose member since entry is greater or equal to 2016. There's one older customer in the database, but it returned just the 2 of them. And as you see, if you run this from any kind of programming language against the database server, you just get a JSON list of 2 JSON objects. And if you have not seen it before, every such object has a primary key, which is stored in the underscore key component, and which is a string. The ID component is also artificially made. It is just a string consisting of the collection name, a slash, and the primary key. And the ref is the revision entry of that. Other than that, you just have those JSON entries you gave when you stored them in the database. Right, so this was nice and easy, and let's just move to the next one. This is an aggregation. If we wanted to just count how many customers we have, we would again just run through the customers collection or specify a complete table scan here, and we just would collect, that's the aggregation statement, the count of the number of customers into this variable, and then we can return, and this shows that you can not only just return documents from the database, you can return arbitrary JSON expressions. So the return value here, well, it's always a list, but in this case it will be a list with one entry, which is a document where there is one attribute called number of customers, and this will be a number, which is the number of documents in this collection. So let's try it out. If I do this and I run it, then I indeed get one element, and this here is one document in the list, and it has exactly as predicted the number 3 here. Right. This time it doesn't offer the table entry because it doesn't make sense to display this in a table way. Right. So that is all still just plain old document queries. The third one is not very different, but it shows that you can obviously combine filter conditions and counting. So this here will just have all the members which became members in 2015, because their timestamp is greater or equal to 2015, and less than 2016. And again, we just count the number of these and return a single document. And if I do that and execute it, then I get the number of new customers in 2015. This is just 1. Execution times can vary a bit, but it's all pretty fast, because I think this expression is actually milliseconds spent to execute this query. Right. You see, this is just a single collection. It's just relatively homogeneous data. We could have done this with any kind of data store. Maybe do one more thing just with the customers. This here is a statistics and aggregation of those over the years. So what I do is I take the substring, the initial substring, hang on, I clicked wrongly. I take the initial substring here of length 4 and aggregate in groups by that. So that is essentially grouping the customers by year. But I'm not interested in the actual customers. I'm just interested in the count for each year. So what happens here is that essentially these aggregations are done. Then I sort by that name in descending order and return one JSON document with the year and the number of customers. And so therefore I would say I expect 2 answers, one for 2015, one for 2016 in the opposite order. So let me just quickly execute this. No, sorry. Statistics sign up and then this. And indeed it gives me 2 documents which are now displayed in table format again. 2 documents, year 2016 and number of new customers 2, 2015 number of new customers 1. So this is obviously pretty boring, and let me just quickly run through this here, which now looks at a different collection. It goes through the items, takes those with price greater or equal to 200, limits the output to 10, and then returns the complete item. Let me quickly run that. And again, I just get a list of 2 elements. And if you look at the JSON, I get 2 things. And indeed, this price is higher than 200 and this price is higher than 200. And that is actually the right answer. Okay, let's go to the next one. Sales. This is the first time that we are using the edge collection with the sales. Recall that there is an edge from a customer to an item if the customer bought this item. So what I do here is simply a collection scan on the sales collection. So I am just looking at edges. This is not yet using the graph functionality. But that's a possibility I have as well. After all, an edge collection is a simple collection in its own right. The members of this collection are documents, and I can do whatever filtering and indexing I see fit. So this here essentially looks at the month of October 2016 and sorts these edges by date and returns all these things. Let me see what it does. There's just a single entry. So on that date, there was a document which returned these 2 things. Note that this thing doesn't return the whole edge, but only a projection. So it only gives you date and billing ID. So this is at the same time an example how you do projections. And let me quickly manually edit this. If I would have returned the whole document as here, no, I have to do this differently. I have to copy the query here. That's not the right query. I have to go to this query, copy it over, and then I can actually edit it in the query editor and say I want to return the whole thing. And this shows you a single document with all its data, in particular with from and to. And since it spotted that I have a subselection of edges, it immediately shows it in the graph viewer, which is not really helpful here, but in other cases it might be very helpful. Right, whilst I'm at it, you can look at the explain here, which shows you the actual query plan. And what this shows you here in particular is that it was using an index to satisfy the filter condition, and the actual filter condition has been thrown out. You see, the filter here has been satisfied by an index because I created a skip list index beforehand. And so therefore in this explain you can see that it does not actually do a full table scan to satisfy this query. And again, I'm asking edges, but I'm not using the graph model so far because I'm simply treating them as documents in their own right. This already shows that it's a very versatile thing to have a native multi-model database because you can even inspect graphs in a document way if you need to. Now, let me show you a join operation. Maybe I want to look at these sales, but I want to actually put in the item data. So let's look at this query. This is how you do a join operation in ArangoDB. The first part is already known. We go through the sales collection. We filter by some date range. We sort by date. But then for every edge we find in there, we just run a simple join operation by saying take all the items, or indeed just the one item, whose ID entry is equal to the to entry of the edge. Recall that a sales edge goes from the person who does a sale to the item which is bought. Well, the person who buys something to the item which is bought, and therefore the to entry of the sale edge must be equal to the ID of the item to actually get the information. And what I can then output is the date of the sale edge, the billing ID, as well as the price, which I fetch from the actual document. Right, let's run this in action. This is now number 7. So if I take this and run it, indeed I get not only the edge with the date and billing ID, but also the complete price. And again, if I take this in the query editor and say I would like to have the complete edge as well, I can just put this here in the JavaScript shorthand notation, execute it, and suddenly I get the complete edge as well as the date and billing ID extracted and the price, which comes from a different collection. So you see here is an example of where I still just query the edge collection as a document collection, but then I use the facilities of the query language to join from a different collection by some kind of foreign key. So that's something which you probably used to do in the old relational database days, and you can still do it now. So I have a few more queries, and this is a more complicated one where we want to show complete orders. Now what we have to do is we have to go through the sales, go through the items, join the item to the edge in the sale, but now do an aggregation based on the billing ID. Remember that all the edges with the same billing ID together make up the complete sale, because obviously in one sale a customer usually orders multiple items at the same time. So the top part here, from here to here, essentially gives you the sales. Now obviously if you have the sale, we still want to join the customers, and therefore we do the same trick again. We run through all the customers and join on the from entry from the edge, and we just have to take the first item in the list of things belonging to this sale with the ID of the customer, and then we can put together whatever thing we want to do. So notice that if we do an aggregation where we aggregate and group by the billing ID, then we can put all the documents, or all the pairs indeed here, into a list items that is dynamically created for each collection we find. And then this join operation can access, and indeed this return operation can access this list. It can look at the first entry or at all of them with the items of star. And it finds the I and the S in here to access exactly the data you need. I know this is maybe a lot to swallow, but I'm happy to answer questions in the end about this. Let's execute this. We get a table. Let's look at the JSON. And again, we get a list of things. The first is a big thing here, and it contains all the items which a certain user bought, namely the user Hugo, or the user actually with name Honk. And this was the total price, and this is a list of items which were in there. So what have we done here? If we just look at the query again, this is not only essentially a twofold join and an aggregation. So this is actually exactly what you would have done in a relational model. Yeah? If your sales would have been a link table between two tables, then this is the same you would have done in a relational database. And you can still do it. And you see, although I'm using the graph model here, if I only have a fixed number of steps, a fixed number of join operations, then quite often actually asking the query engine to do a join operation is faster than a graph operation. The graph operation is very, very good if you don't know beforehand how deep you have to go. And here, you could have done this with graph facilities, but you can also do it in this way. So you see, there's a lot of choice in how you do things, even if you have fixed your data model. Now let's get back to the graph functionalities. I have 3 more queries before we end this talk. And this here finds the top sellers using the graph functionality. So what do? We run through the items. For each item, we find all the buyers. How do we do that? Now remember, this is a graph model. The arrows are pointing from the customers to the items. So therefore, if I go in the sales graph 1 step backwards from the item, I find all the people who have bought that. And what this does, it runs a subquery here in brackets to find all the people who have bought a certain item. Then we only look at their number. That's the length of this variable here. We sort in descending order, and we put out the description of the item, the order ID, and the number of sales. So let's run this. And indeed, if I do this, I get that in my little toy example, the item with description chair with this order ID has the most sales, namely it was 4 times mentioned as the outgoing or as the incoming edge from some customer to the chair. So that's now the first time we have a graph query. And let me just point out that the syntax in AQL is very natural. What you do is you use the same for syntax like you would for a collection scan or for running through a list. But then you have a range of depths. And in here, I just have depth 1. You say the direction, which can be inbound, outbound, or any. You specify the graph or indeed the edge collections. You give the starting thing, which is here the item. And then you return. And then you have just a simple AQL cursor as you would. So this shows that the graph querying possibilities are really embedded naturally in the AQL language and can therefore easily be mixed and matched with other things like joins or collection scans or index lookups or whatever. Right. Now, for example, the other way around, you can just start from a customer and find all the items he has bought. Now, how is this done? You start with your customers, you put in the ID of the customer here, you fetch the 1 document, and now you run a graph traversal of depth 1, this time in the outbound direction, that is going from customers to items. And you collect by order ID. That's the item the person bought. And then you get which customer bought which item, how often, and you also add the description. This is just the number of times the person has bought it. And so let's run this in practice. We'll go here. I see this, and again, JSON documents. So you see you get a list. This is the order ID of the item. The description is a table. It was bought one time by the customer Hugo. That's the one we started with. And then he has bought something else, another order ID, another chair. Again, you have the full customer information, which I just embedded here. And you have the count 3 and the description, whatever you want. So this essentially shows a simple graph query. And imagine you have a graph model where you have deeper paths or longer paths or whatever kind of nested pattern matching for graphs. This is just an easy example how you could do that. So let me close with the most complicated of the queries I showed today, which is about finding recommendations. So if you want to recommend things to buy for one customer, a very simple idea is the following. If you have a customer, you might see what that customer has bought. Then you would like to see which other customers have bought the same thing. And then you would like to look at the place where this customer is, the second customer, and see what they bought. And the thinking is, if two people have bought the same thing, and one of them has bought something else, you possibly want to recommend to the other guy what this guy bought. Well, it's a guess, but that's what you do with recommendation engines. And how is this done? Well, this is now a graph query of depth 3. Since we model the sales with an edge from a customer to a thing, this is now going in any direction from customer to thing, back to customer, forward to another thing. And this is done in this way. In this syntax here, I do a graph traversal starting from my customer, in this time customer Lulu, in the sales graph. And I go 3 steps, at least and at most. I have some options for the traversal. I don't want to edge. I don't want to have unique edges or vertices, but I do not only want the vertex at the end of the path, but I also want the latest edge in the path, and I want the complete path. So when I do this and the graph traversal finds all possible ways to go 3 steps from Lulu, then the path has documents for the vertices and edges I visit along the way. And so therefore I can, for example, do a filter condition to say the third vertex on the path, that is after the second step, should not be identical to the key of the customer. So that means I don't want to go back to Lulu, I want to go to somebody else and then to some item. And what I do here is I just put together some data from all these possibilities, and that gives me a first list of things I might want to recommend to Lulu, again on the basis of thinking that she wants to buy the similar things which other people who have bought things she has bought, but what they have bought as well. So let's run this. And here we go. This suggests that there was a path from Lulu to a chair to Hugo backwards to a table. So this means Lulu has bought a chair. Well, this chair was also bought by Hugo, and he has bought a table. So maybe if Lulu has bought a chair, we recommend to her to buy a table as well. Okay, I know this was just a very tiny toy example, but let me just say I wanted to show you some AQL, I want to show you some user interface and ArangoDB in action, and I wanted to make the point that a multi-model database, a native multi-model database, gives you a whole lot of possibilities for your data modeling. And the fact that you have a single query language which links the 3 data models and allows you to mix and match and do whatever queries you see fit from any language you are using ArangoDB with, is a very powerful technique indeed. Now, the last page here has some links about things we have set up for you. And this is essentially the end of my talk. Let me just mention two more things. You know, ArangoDB is an open source project run on GitHub, but it's also a company behind that. And if you want to help us somehow, then the very easiest thing to do is that you star us on GitHub and put the skill ArangoDB in your LinkedIn profile. It sounds strange to ask this thing, but these are two of the important queries how open source models, open source projects can somehow measure their success and their reach. And for you, it's quite easy. You just click star on GitHub, or you put the skill ArangoDB in your LinkedIn, and it helps us a lot. Right, and the other thing I want to mention is that apart from my questions, I'm now happy to answer on the live chat. I will switch over there in a second. Is that towards the end of this month, our CTO, Frank, and other senior developers will run a question and answer session at some date. The date is not completely finalized, so if you want to get it and don't miss it, then just keep an eye on our Twitter feed and maybe subscribe to the ArangoDB newsletter, because it will all be announced there. Right, so anyway, this ends my talk, and I will now switch to the live chat, which I can see now for the first time. And so let me try to answer things here. Now we have the problem that whatever I see and type, and when I directly speak about this, will then be 30 seconds later visible to you. So let me try to answer things here. And regarding the keyboard, the microphone noise, I definitely hope that this has improved by now. But it is possible that if I type now, there will be more noise. Right. So I'll answer the question, can you give also an example of a key value model in HUL? Essentially, well, should I type or should I speak? Well, if you run something like this query here, and just you say let customer equals document, then this already does a key lookup. Because if you just ask for document, then it simply does a key lookup of this identity in the corresponding collection. Another possibility is a query like this here. If you just filter on ID. If you would replace this filter statement by a filter c._id is equal to something, then the query optimizer behind the scenes would just do a key value lookup. And if you think about it, what such a join operation does, where is it? Here's one. Then this actually, behind the scenes, uses an index on the sales collection to filter entries here, and then does a key lookup in the items collection to perform this join operation. So in a sense, the key value model is used in these join operations, for example, or if you do it explicitly, and this should give you an example. Right, so there's the next question. Do you recommend using predefined graphs as much as possible? I currently have been running graph queries using vertex collections. I don't actually understand what predefined graphs are. So I hope that the delay will not be too large. Let me just point to the next question. Can I build an auto-completion system with ArangoDB? Did any of your clients ever done this? I was using Elasticsearch completion suggester for that purpose before. Well, an autocompletion would just be a special type of query you send. You probably do get whatever the user has typed, and your client application would send a request to ArangoDB to quickly give suggestions for the completion. So we have not done anything prefabricated for this, but I think it would be relatively straightforward to send queries. And if you limit the number of results, the response should be pretty quick. We do have a full text index, which might be useful here. And but we probably don't have as many facilities as Elasticsearch. After all, Elasticsearch is a search engine, so it specializes in this kind of search. So I turn to the next question. Do I have to use graph collection for joins, or could I use typical primary key, foreign key relations between two documents? The answer to this is definitely you do not have to use graphs. You can simply use a document store like ArangoDB in the way you would use a relational database. You can just set up your document collections, not mess about with any graphs, and do exactly the type of query I did using primary key and foreign key. And so the answer is clearly yes, you can. I didn't have an example of this in my presentation, but it could easily be done. And but you see examples of this just ignoring that things are edges. Yeah. Okay. So I still don't really understand the question about predefined graphs. Let me see. When you store a graph in ArangoDB, you should definitely have at least one vertex collection and at least one edge collection. You can have multiple vertex collections and multiple edge collections. And the question probably refers to the fact whether you have to set up official graphs to use that or not. The recommended way is that you do set up a graph, but it's not strictly speaking necessary. The AQL syntax allows to run graph queries if you simply give the edge collections in the place where you otherwise would say graph and then in quotes the name of the graph. So you can just use the edge collections. The trouble with this is if you don't predefine the graphs, is that the query can beforehand, before actually doing the graph traversal, has no chance to derive which vertex collections are going to be used. Because in principle, any kind of edge can refer to whatever collection is out there. So therefore, if you only use the edge collections in your AQL query, then what you should do is you should mention all the vertex collections with the using command in the query. So for example, if your vertex collection would be called V and your edge collection would be called E, then it's fine to do the graph query just by using the edge collection E, but then you should have a using V statement in your AQL query. And I think in the cluster, you even have to do that because then the cluster has a way to know which collections to actually refer to. I see. Okay, finally, I get the thing with the question about prefix trees. Yes, indeed. What you could do if you have, if you want to implement an engine for auto-completion system, you could actually store the prefix tree in ArangoDB as a graph. Now, if then the user would type something like ABC and you send a query to the database, you would now run a graph traversal with depth, say, 3, because you have 3 letters in here. This would bring you to all the different positions. You could go in the prefix tree, and you could do that. The question would then be how you limit somehow whether the number of results is something you want to actually return to the user. But I think you actually could do this, and it's probably not even a bad idea. I haven't thought about this, but I think the answer is you could. Let me just in this context mention one more thing. Another feature of ArangoDB is that it is extensible by JavaScript code. We have something called the Fox framework, where the idea is that you can deploy your own JavaScript code on the database server. And this question about auto-completion sounds as if it is best implemented as a little data-centric microservice in ArangoDB, and you would probably want to do this with a little Fox app, which knows about the prefix tree and your actual data model, and which has its own little URL, its own HTTP route, and therefore you can extend the HTTP interface of ArangoDB with your own route, which does exactly whatever you want. This way, you have the complete power of a programming language, but the code is executed on the database server with direct access to graph traversals, AQL, and possibly other things you want to do. And I think in this case, you could very quickly come up with a strategy to get the right recommendations for completion. Right. So I hope I have answered this. It's a bit awkward with this delay. Aha, I see another question. Is Fox like stored procedures in Microsoft SQL? Well, it is similar, but I think it goes well beyond that. In stored procedures for SQL, you can only store SQL statements. So you can store prefabricated SQL queries and execute them. Here, you can do much more because you can deploy your own code. And for example, you can implement whatever kind of program you need in this code. So in principle, you can, for example, do web queries, queries to another database. You can do additional logging. You can do additional authentication. You can kind of attribute level authentication in the database with direct access. So it is JavaScript code. It's executed in the V8 engine we embed, but it has directly access to the C++ engine. And so therefore, you have the complete power of a complete programming language to do really whatever you want. You can do multiple queries, you can do one query, see about the result, and then decide what other queries you want to do. You can mix the data models, you can access single documents, and you can even do other queries to other data stores yourself. So I think it goes very, very well and much further beyond what stored procedures in SQL can do. Right. So I think we are over 1 hour now, and I think I'd like to terminate this. I'm happy to answer other questions later on. And so just thanks for listening. Thanks for listening the recorded video, and even and again, you can download the video, the slides, and everything. Just go to YouTube and look at and follow the links there. Thanks.